Okay, in chapter 6.2 I want to do the following thing: design PID control algorithm with method conversion of differential equation into a difference equation. No use of Z transform. So this is a method which use the differential equation of any system, and I show you tricks where, for example, the dx over dt are converted into a digital algorithm, or where an integration of x dt is converted into a digital algorithm, because the PID differential equation looks like this. Yeah, if you have a controller, you should know, okay, the controller has input xd and output y, and a PID algorithm can be written in y of t is k times xd of t, that is the proportional part, the p part, plus ti times integration of xd of t dt, that is the integration part, plus td times dxd over dt. This is the differentiation part. Okay, I have made a small error, sorry for this. I wipe the coefficient of the integration because this is wrong, because this must be written as 1 over ti, because the integration gives the unit t, and of course then this should be unitless. If you compare this with a transfer function, which we can find in the workbook of Control System 1, look in the paper. I open the workbook of Control System 1. On page 20, you can see here a transfer function of the PID T1 controller. T1 means there is an additional PT1 part. For the numerator here, the numerator is the differential equation of the summing form of the PID, and you see again I have forgotten to parentheses, so I should add now these parentheses, and this exactly then comes from transfer function PID. I just copy this, y of p output divided by xd input is called the transfer function f of p of PID, which is, if we look into workbook, is k times 1 plus 1 over pt1 plus p times td. So this is k, parenthesis open, 1 plus 1 1 divided by PTI plus PTD. Yeah, you see the relation between differential equation here and transfer function here. The factors are the same because the conversion from time into frequency going by Laplace transformation is linear. The integration is converted into a 1 over p in frequency, and the differentiation is converted into a multiplication with p in the frequency domain. So this is just a repetition of that what we have learned in control system 1. And this task today is to convert now this equation into a digital algorithm. So we start with a p, followed by the integration conversion, and end up finished by the differential conversion. Okay, so first point is 6.2.1 P controller. A P controller has a very simple differential equation. There is xd input, y output, y of t. Looking here, there is no integration, no differentiation. Y of t is k multiplied with xd of t. This of t means that it's a function of t, a time function. Dynamical system, k is a constant, the P controller gain. Now, in our digital system, I go back to the control system paper. Note that my input signal x or xd is now converted from a continuous time signal x of t into a time discrete value x of n. So what we can write now is I convert by sampling. I get y of n to only to the time points n times to, in short written as y of n, is what? Is the controller gain k multiplied with the control difference of n. So what we have is a very simple system. I sample the control difference, I sample the process output, of course, process output of n, and subtract from a desired value. Sorry, xd is desired value w of n minus measured value x of n. So this can be calculated before each calculation. This gives the control difference xd. So this is a value in a variable, and now I have to multiply this value just with the k factor. What I need now is in the algorithm I have to calculate. I read now what I have to do. Reading. I have to calculate the output value y, which I then can send to the digital to analog converter in the way that I sample the actual control difference, multiply with k. Y new DAC output is k multiplied with actual control difference. This has to be done in each step. So for each sampling time you have to multiply your measured value with the k is a floating point number. You need floating point multiplication. So that is the only thing what you have to do in multi, and then you can write the algorithm in let's say C language. Yn is equal k, and the multiplication in C language is this asterisk sign times xd. So that's the line, the command line in a C program where you realize the P algorithm, and this of course has to be done each sampling time. So if you sample with 1 millisecond, this has to be done 1000 times a second, and that's all. So you have your P controller. Now let's continue with the I controller or integration algorithm. In chapter 6.2.2 you see the integrator works with an integration of the control difference. So this integration must be realized as a digital algorithm. The prefactor here you see is 1 over ti times k. Independent of this, I just convert the integration signal, and then we can use the complete equation to calculate the complete algorithm. So in the I controller, I want to have an output signal, say u of t is integration of xd of t dt, and the integration works from 0 to say special time t, say 1, and I want to have now the conversion of this. First I make this my solution can be explained very easily in a graphical representation of the integration. So what we do is the following: I make a small diagram. Horizontal axis is t and vertical axis is xd, and we assume that we have a curve, a continuous curve of my control difference signal. Now I sample this signal with sampling points, and the distance of one sampling point, this is our sampling time t sub. Okay, you see this works in this way, that the computer only gets this information, and assume this is the actual time point t1, and I want to have now the integration from starting point 0 to actual time t1, and you know the integral of this xd of t dt is nothing else than the area under this curve. So I can just make an indication of this. The area is integration 0 t1 xd of t dt. That's the analog integration. Okay, now what we can do is very simple. We can approximate, we can approach this area by using rectangles, sum of rectangles. Okay, and we can say, okay, these values are available. This is xd of 0. I call this last point here, this is this is the time point n, the actual time point n. This is xd of n. This here is xd of n minus 1, n minus 2, n minus 3, and so on, xd of 0, xd of 1, and so on. So we know, okay, we're starting from 0, ending at time point n. And what we can say, okay, this area is approximately equal what? Sum of the area of each rectangle. The rectangle has the horizontal dimension t sub o, and the vertical dimension is the actual xd value, say of I, and the running index of course should start with 0, with this value. So the I0 value gives the area of the first rectangle. And now you see what I can do is two versions. I can stop with the approximation of the area with this xd n minus 1 value. Then I have the last rectangle is this. So we can say, okay, until e is n minus 1. This is the area like this. So we can say, okay, this is in yellow. We can say, okay, yeah. So it is the yellow version, but we can do also another thing. We can say, okay, the last value xd of n is known. Why not add the last rectangle curve like this, the green area, green. So we can say the area is approximately equal, e starts from 0, running up to this time n, t0 times xd of I. So this, the area which carries the last rectangle, and this is the area without the last rectangle. So this is a little bit smaller than this, is a little larger than this. We can say the area of the correct blue version is the exact area under the curve. The yellow is a little bit smaller, the green is a little bit larger. So the result is there are two different versions of I algorithm. You can find in literature either this version or that version. There is not a clear argument which is now better. In my paper you can see that I prefer this version, so I call this is a Bayerline version, the Bay version. I have a colleague some years ago, Mr. Baumann, in his papers you can see that this version is used, and he gets algorithms using only the yellow rectangles. So this is the Baumann version. Yeah, so in my paper I work both versions finally through to the algorithm. Today I only want to show you the my Bayerline version. What happens now with the replacement of the integration by this sum? Can we use this as a programmable algorithm? So what we can write down is u of n finally, so the Pi version, un is replacement of integration is integration from 0 up to n x d of I. Oh, make it a little bit better. XD of I times sampling time. Of course, this sampling time can be extracted out of the sum because the sampling time is in all rectangles the same value. We can extract it out of the sum and get finally this equation. Can we program this? This algorithm? What have we to do? The output, which then is sent to the DAC, is a multiplication of sampling time, no problem. We have to calculate the sum. Okay, what does that mean? The sum means I have to add all control difference values starting from the switch on of the computer until the actual time. Imagine what that does mean. For example, if you have a sampling time of 1 millisecond, you get 1000 values a second. After 1 minute, you have 60,000 values. After 1 hour, you have 3.6 million values. So the number of values will getting larger and larger. And anytime you have to calculate the sum, you can understand that this is crazy to program this directly with the sum. We have to find another method, another way to avoid this sum, which has increasing number of values. You have to store them, and the problem is, or the problem not, the idea is all old values won't change, are still the same. Why should I add all values again? So there is of course a better version which I show now. We use the method of recursive algorithms to optimize this integration algorithm. But that will be done in the next part. This video ends up here. See next part 3.